Hello again everybody. In today's video, we're going to try to use each of the four kinematic equations, starting with this one right now. A ball is thrown up at some initial velocity from the height of my head and is allowed to fall to the floor. How much time did it take for the ball to reach the floor? And here I have a little doodle of myself throwing a ball up, and this ball, going at some initial velocity upwards, is going to reach some maximum height. We don't know what that is. But at this point, we don't really care about that. We only care about the time that it took to reach that maximum height, and then eventually it's going to drop back down. So let's calculate that first. We can already use one of the kinematic equations. This would just be v is equal to some initial velocity plus at. The final velocity, once it reaches the height, or the maximum height, will just be 0, so we can just cancel that out. Now, we just have to solve for t. We get minus v naught is equal to at, and then we solve for t. Minus v naught over a. And in this case, a would just be negative 9.81 meters per second squared. That's just the acceleration. And of course, both of the minus signs cancel out, so time is always positive. Remember that. Something very interesting happens at this point. The time that it took for the ball to go up to its maximum height is also the same time that it takes for the ball at the maximum height to go back to where it initially started. So that little section up there, we can just multiply by 2t. I'll just say that this is t part 1, because we're going to do part 2 in a little bit, once it reaches the floor. The time for part 1 is just negative 2 v naught over a. So that's going to be the first part. Now we need to take into consideration, from the point of my hand, and the ball is going down at this point, how much time does it take for it to reach the floor? Now, something very interesting happens once the ball reaches the point where it initially was thrown up. Once it was thrown up, and then it comes back down due to gravity. At this point, the ball is going towards the floor at the same velocity that it was thrown up. So this will just be v naught again, but this time in the downward direction. And of course, there was some height here. And now we're able to use the second kinematic equation to solve this. For this problem, it would be delta x is equal to v naught t plus 1/2 a t squared. And let's plug in a little bit of what we have so far. This will be h. And remember, this is going in the downward direction. So it is minus v naught this time. T plus 1/2 a t squared. Now this isn't so useful since we are trying to solve for t. However, we can rearrange this into something more useful once again. So this will be 1/2 a t squared minus v naught t minus h is equal to 0. Now this equation should look a little bit familiar. This is actually just the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And to make this even more obvious, this will be your a, this will be b, and this minus h will be c. So let's try plugging that in. So the final result that we're going to get is t for the second part, I'll say t part 2, is equal to v naught plus or minus the square root of v naught squared plus 2AH divided by A. Now, of course, we need to remember one more time that time has to be positive. I know in the quadratic formula there's a plus or minus sign, however, the result always has to be a positive time. If we wanted to actually conclude this entire problem, all we would have to simply do is add t part 2 plus t part 1, and there you have it. We've used the first two kinematic equations for one single problem. Alright, let's move on to the next two. Let's try and analyze a graph to use the kinematic equations. So here we have an airplane that lands on a runway and its velocity has been recorded. How much distance did it cover? Well, this is going to be separated into two parts. The first part is when the airplane lands on the railway and it starts to deaccelerate, and then it starts going at a steady velocity until it stops. So let's just calculate the first section. The first section will just be delta x is equal to some final velocity plus some initial velocity over 2, and that is just multiplied by t. So let's just plug and play here. The final velocity for the first section, we'll just say x1. That is just v1 plus v2 over 2. And for the times, we're just going to say that is the time at point B minus the time at point A. That is the total time that it took to deaccelerate. Now if we look at the second section, where it just had a constant velocity, that will just be velocity 1 plus another v1 over 2. And this time the time is just the difference between the time at point C minus the time at point B. And there you have it. So in order to answer how much distance did it cover, all we have to do is add x1 plus x2. Now let's move on to the final kinematic equation. Car A starts with some initial velocity and accelerates to some final velocity. Car B can accelerate twice as fast as car A. How far did car B travel compared to car A? Well, let's begin by using our final kinematic equation for this one, which is just v squared is equal to v naught squared plus 2a delta x. And since we're solving for two of them, let's just call this x sub a for car A. And solving for that, we would get 2a delta x sub a is equal to v squared plus v naught squared. And solving for delta x for car A, that would just be v squared plus v naught squared over 2a. Now let's do the exact same math for car B. V squared equals v naught squared plus 2. Now we did say that car B can accelerate twice as fast, so this would just be 2a times delta x sub b for car B, and when we do all of that algebra, we would get x sub b is equal to v squared plus v naught squared all over 4a this time. So if we just compare the distance that it took for car A to accelerate to car B to accelerate, there's only a difference of an extra 1/2. So actually just x sub b would be a half of the distance of x sub a. And there you have it. We've used each of the kinematic equations, and you are now ready to rock and roll in your tests. Good luck out there.